So we're given this expression for f of x, saying f of x equals 3x cubed plus 2ax squared minus 4x plus 5a. And given that x plus 3 is a factor of f of x, find the value of the constant a. We can also see it's a 3-mark question. Whenever a question talks about things like factors or gives things in the form of brackets like this, it quite often includes the factor theorem. Now the factor theorem states that when f of k equals 0, then x minus k is a factor of f of x. So we can see in our definition of the factor theorem, we've got that x minus k is a factor. However, in the question they've given us x plus 3. So we can rewrite that as x minus 3. Because when you take away a negative number, you're essentially adding it. So this means that our k value in the factor theorem is minus 3 here. So sort of reverse engineering the factor theorem, we could say that we know that f minus 3 must equal 0. So doing that, we can set up an equation. So if we say f minus 3 equals, and here we're going to replace all the x's with minus 3. So 3 minus 3 cubed plus 2a minus 3 squared minus 4 times by minus 3 plus 5a, and that equals 0 because of the factor theorem. So multiplying out these brackets, we've got 3 times by, so minus 3 cubed. So minus times a minus times a minus gets a minus, so it's a minus, and 3 cubed is 27, plus 2a multiplied by, so a negative times a negative is a positive, and 3 times 3 is 9. Minus 4 times minus 3, so we get plus 12, plus 5a equals 0. Now we're going to just multiply out the rest of the brackets. So 3 times minus 27 is minus 81. Plus 9 times 2, so 18a, plus 12, plus 5a equals 0. So now what we can do is collect like terms. So we can collect together both the a's and both the constant. So adding the minus 81 and the 12, we get minus 69. And then the 18a and 5a, we get plus 23a. And that all equals 0. So now we're going to solve this to find the value of a. So if we add 69 to both sides of the equation, we get the 23a equals 69. If we then divide both sides of the equation by 23, we get that a equals 69 divided by 23, which simplifies down to just be 3. So therefore, our answer is that a equals 3. And look in the mark scheme to see where we'll get the 3 marks from. We get a mark for this step here where we attempt f of minus 3 and then set that equal to 0. We also then get the next mark for setting up this linear equation and then solving it for a. And then we get the final mark for getting the correct answer for a. So figure 1 shows a plot of part of the curve with the equation y equals cos x, where x is measured in radians. Okay, so I'm just going to stop there quickly, and whilst we're here we can see that we've got y equals cos x on figure 1, so I'm just quickly going to label this on figure 1 before I forget. So look at part A, it says use diagram 1 to show why the equation cos x minus 2x minus half equals 0 has only one real root, giving a reason for your answer. So you can see it says to use diagram 1, so we're going to have to graphically show this using diagram 1 somehow. But we also need to give a reason for our answer, so we're going to need to use some words to explain it as well, in order to get the 2 marks for the question. So we've been given the equation here, and we're just going to have a quick look to see what we can do with that, and see if we can manipulate it anyway. So the first thing that jumps out to me is that we've got the minus 2x and minus a half. So if we rearrange the equation, we can say that cos x equals, if we add the 2x and add the half, we've got equals 2x plus a half. Now we could look at this and think of this actually as 2 separate functions of y. So we can say that y1 equals cos x and y2 equals 2x plus half. And think of these as 2 separate functions. When we equate the functions, so set them equal to each other as we've done here, the point of intersection of them graphically on the graph will be solutions to the equation. So if we only get one intersection between both these functions of y, then we know this equation will have only one real root. However, if it has more intersections, then we know there'll be more real roots. So for example, 2 intersections will mean there are 2 real roots. So what's great is that we've already got the function y equals cos x graphed out here. So I'm just quickly going to edit this to make it a bit clearer. So we've got the y1 equals cos x. So now we're going to plot y2. So if we think about this quickly, we can do a couple of points to help us. So if we sub in x equals 0 to give us the y-intercept, we get that y is a half. So if I just plot that on here, and then working down here quickly, we could also work out the x-intercept. So if I say set y2 equals to 0, we get 0 equals 2x plus a half. So we say 2x equals minus a half. And then x equals, so if we divide both sides by 2, we get minus a quarter, like that. Brilliant. So I'm just going to plot that on here, sort of roughly, about there. So that's great. So now we've got these two lines. I'm going to try drawing y equals 2x plus a half. So if I do that, we get a line something like that. I'm just quickly going to label it on so it's easy to remember. Now, one of the checks to make sure we've sort of roughly done it right is we can see here we've got a positive gradient of 2, which matches up with the line we've drawn. So as I mentioned earlier, the points of intersection will be the solutions to the equation. And we can see here we've got one single point of intersection here, which means we only have one real root. So we've used diagram 1 to show this, but now to get all the marks we need to give a reason for our answer. So down here I'm going to write an explanation. So since there is only one point of intersection between the functions y1 equals cos x and y2 equals 2x plus a half, it follows that the equation cos x minus 2x minus half equals 0 has only one real root. So looking back to see where we get the marks, we get 1 mark for drawing a graph like this. And we get the second mark for an explanation like this. But the key points you need to include in the explanation is that there is only one single point of intersection in order to get both the marks. So what we're now going to do is work on part B. So it's given that the root of the equation is alpha and the alpha is small, use a small angular approximation for cos x to estimate the value of alpha to 3 decimal places. And remember to 3 decimal places because it often specifies in questions how they would like that answer, and you could lose silly marks for writing it in the wrong form. Okay, so looking back up at part A, we can see we're given this. So we're going to use this same expression again to estimate the value of alpha. Now from the formula booklet, we know that the small angular approximation for cos x is that cos x equals 1 minus half x squared. So what we can do, we can use this sub into the original equation, or the one from part A. So doing that, we've got 1 minus half x squared minus 2x minus a half equals 0. So it's great because look at this, we can start to see that it's a quadratic. Now before we solve it, we can tidy it up a little bit. So if we take away the half from the 1, we get minus half x squared minus 2x plus a half equals 0. And tidy it up even further, if we multiply by minus 2, we get x squared plus 4x minus 1 equals 0. Now what we're going to do is solve this. So these sort of questions aren't trying to test your ability to solve quadratics. So we don't need to be worried about trying to use the quadratic formula perfectly. We can just put it into our calculator to get the solutions. So putting this into the calculator, we get that x equals minus 2 plus root 5. And x equals minus 2 minus root 5. But here's where questions sometimes often try and catch you out, because here we've got two solutions. However, we know from our work in part A that the equation has only one real root. So we can have only one value for x. So now we need to work out which one to reject and which one it can't be. Well, looking back at our diagram at the top, we can see, so this is where it intersects, so this is where the solution is. And we can see this gives us a positive value of x right here. So we know that this value of x we can reject. So it's always good to still write it down, but just say that we reject it. So therefore, the root, or as it calls it in the question, alpha, is approximately equal to, and remember it says in 3 decimal places. So again, using our calculator, we can see that it's approximately equal to 0.236 to 3 decimal places. And that's the answer to the question. So looking back to when we get the marks, we get 1 mark for this step here. So using the small angle approximation and subbing it into the equation. And we get the second mark for attempting to solve this quadratic equation. And we get the final mark for getting the correct value for alpha. So look at the question, we're given an expression for y. So y equals 5x squared plus 10x all over x plus 1 squared. And we're given a condition that x can't equal minus 1. And part A says we need to show that dy by dx equals a over x plus 1 to the power of n, where a and n are both constants that we need to find. And this is a 4-mark question. So essentially what we need to do is differentiate this expression for y. Now there are several different rules for differentiation that we can use. However, in this case I think we're going to use the quotient rule. And there's a snippet of the formula booklet here, and the quotient rule is actually in the formula booklet. And I think the quotient rule will work here well because it's in fractional form. So we've got a numerator over denominator, which is the same form as the quotient rule. So we're now going to use the quotient rule to help us. So if we write f of x, and we're going to set this equal to the numerator, and then we're going to write out g of x and set this equal to the denominator of our expression of y. Now the reason I'm doing this is, as we can see in the snippet from the formula booklet, I'm sort of just matching up how they look in the formula booklet so I can use it to help me. So we see in the formula booklet as well, to work out the derivative of y, we're going to need to know the derivative of f of x and g of x. So if we work those out now, f dash of x, and all this notation means is sort of differentiating. So f dash of x is the derivative of f of x. So to differentiate this, okay, so we've got 5x squared. So we're going to bring down the power and times it by the 5, so we get 10. So we get 10x, and then we take 1 away from the power. So 2 take away 1 is 1. So it's just x. And again, we're going to do the same for the next part. So we've got the power of 1, we're going to bring that down. So we get times it by 1, so you just get 10 again. And take down the power, so 1 to 0. Anything to the power of 0 is just 1. So this is our expression for f dash of x. We're going to do the same for g dash of x. And this time it's a little bit more complicated. We're going to have to use the chain rule. So using the chain rule in this, first thing we need to do is the same as normal. We're going to multiply down the power and bring it to the front. So we've got 2. And then we need to multiply this by the derivative of whatever's inside the bracket. Well, the derivative of this is just 1, because the derivative of x is just 1. And then a constant, when you differentiate something, the constants just go. So we've multiplied that by 1. Now the last thing we need to do, we need to multiply that by the whole expression, but take 1 away from the power. So this means you get x plus 1, and 2 take away 1, so we get 1. So that equals to x plus 1. Now in this situation, this actually worked out quite simply, because the derivative of inside the bracket was just 1, so it didn't make a difference. However, often it does make a difference, so you've got to be really careful when using the chain rule. So writing this down over here, we've got 2 multiplied by x plus 1. Brilliant, so now we're actually going to use the quotient rule. So we can say that dy by dx, so we have f dash of x, so that's 10x plus 10. Multiplied by g of x, so x plus 1 squared, take away f of x, That's 5x squared plus 10x multiplied by g dash of x. So that's 2. So what I'm actually going to do to make it a bit easier is I'm going to insert the 2 here. So it's multiplied by the 2 and then times the x plus 1 here. Fantastic. And that's all over g of x all squared. It's x plus 1 squared all squared. However, using our rules of indices, we know that this we can simplify down to just being to the power of 4. Also, notice the use of brackets here. Using brackets like this will make it much easier when we're expanding out. So we want to expand this out and simplify it. However, we don't really want to expand all this because it'd be a big mess. So we want to try and look to see if there are any things we can do. And there is actually. We can see that we've got a common factor of x plus 1. So we can take out a common factor there, there, and there. So I'm going to write that out below so it's just a bit simpler to see. So now what I'm going to do is expand out the brackets in the numerator and see if anything sort of cancels out with each other. So we have 10x times by x, we have 10x squared. Plus we've got 10x times 1, so we have 10x. Plus 10x again, because we've got 10 multiplied by x. And plus 10, because 10 times 1 is 10. And then we're going to multiply this 2 with both parts of the bracket. So you're going to have minus 10x squared and minus 20x. And again, that's all over x plus 1 to the power of 3. Oh, this is great because we've got lots of things which look like they might cancel. You see, if we combined both these 10x, we get 20x. And we've also got a minus 20x over here. So this minus 20x cancels with both these 10x's. We can also see here we've got a minus 10x squared, which cancels with the 10x squared here. So it's really simplified it down. And in the exam, make sure you're clearly showing what cancels out with a simple line like this. But make sure you can still see what's behind the thing you're crossing out, because you can get some marks for it. So if I write this out one last time, we're left with 10 all over x plus 1 to the power of 3, which is the answer. Now looking back up in the question, we see that it says show that dy by dx equals a over x plus 1 to the power of n. Well, this is great because we've got this in the correct form, and we've got a value of a being the constant is 10, and the value of n being 3. And that's great because they're both constants, and it says in the question that a and n are constants to be found. If we got a or n not to be constants, or we got dy by dx in a different form, we know we've likely made a mistake, so we can go back and find a mistake. But we got it in the correct form, so that's great, so we know we're on the right tracks. And it's been great because we've shown all our workings. It's a show that question. So looking through to where we get the marks, you get 1 mark for using a correct method of differentiating. So in this case, we use the quotient rule and attempting to do that on the expression for y. So we've got 1 mark here. We got a second mark for this step here. So where we wrote out an expression for dy by dx using the quotient rule. However, it didn't need to be simplified. So before we cancelled the x plus 1. We then get a third mark for this step here where we do simplify it down and factorise or cancel out the x plus 1, attempting to simplify. Then we get the final and fourth mark right here where we get the correct simplified expression for dy by dx. Right, so we worked through part A and we found out what dy by dx is. Now we're going to work through part B. And part B says, hence, introduce the range of values for x for which dy by dx is less than 0. And this is just a 1 mark question. We can see in the question use the word hence. So it means that we need to use what's in part A. So our answer from part A when trying to answer part B. So it says dy by dx is less than 0. Well, we know what dy by dx is from part A. So now what I'm going to do here, part B, is I'm just going to replace dy by dx with what we worked it out to be. So that's 10 over x plus 1 to the power of 3 is less than 0. Brilliant. Now this is what we're going to try and solve and find the range of values for x for which this is true. Now we need to sort of think about this quite logically. If we think about this, less than 0 essentially means negative. So we need to work out when, for what values of x, this expression is negative. Now we see it's in fractional form, so we're just going to try a few things. in fractional form, if you've got a positive over a positive, well, that equals a positive. So that is greater than 0. If you watch a positive and it's over a negative, that equals a negative, and that's less than 0. So we can see up here that this number is positive in the numerator, therefore the denominator needs to be negative for this condition to ever be true. So we're going to break this down even more. So essentially what we're now saying is that x plus 1 to the power of 3 needs to be negative, so it needs to be less than 0. So now we've got a new inequality. Right, so now we're going to think about this in a similar way again. So we have something to the power of 3. If we have a positive number to the power of 3 equals a positive. We have a negative number to the power of 3 equals a negative. So we need, breaking this down even further, x plus 1 should be negative in order for x plus 1 to the power of 3 to be negative, in order for 10 over x plus 1 to the power of 3 to be negative, or as it's saying here, less than 0. So writing this out in a clearer way, we've got x plus 1 needs to be less than 0. So if we take away 1 for both sides, we get x is less than minus 1. And that is the answer. Also, just a quick check, if we look back up in the question, we can see that we've got a condition that x can't equal minus 1. Well, fortunately, it's good because in our final inequality here, x doesn't equal minus 1. It can't equal minus 1. However, in other questions, you might get an answer where it did equal minus 1. So you might need to adjust your range in the final answer, looking back up at the question to see if there are any extra conditions you need to be aware of. So this question was quite a lot of work. However, it's only 1 mark question. So looking at where we'll get the marks, you just get the 1 single mark for getting x is less than minus 1. So part A says, find the first 3 terms in ascending powers of x of the binomial expansion of 1 over the square root of 4 minus x, giving each coefficient in its simplest form. And this is a 4 mark question. So look at this question. The first thing that stands out to me is that we need to find the first 3 terms. And quite often in binomial expansion questions, it will tell you how many terms you need to find. So make sure you look out for that in the question. So first thing I want to think about is there anything we can do with this expression to get it into a form that will make it more suitable for carrying out a binomial expansion? So the first thing I want to think about is our indice laws. Now we know that if we do a to the power minus 1, that's equivalent to 1 over a. In a similar way, if we do a to the power of a half, that's equivalent to the square root of a. So sort of combining them together, a to the power of minus a half is equivalent to 1 over the square root of a. Okay, so look at that, that's great, because we can see here, this is actually a really similar form to our expression up here. So I'm going to rewrite our expression up here as 4 minus x to the power minus a half. Okay, fantastic. So this is starting to look like something we can work with. If we look down here, we can see that I've brought in a little snippet from the formula booklet. And this is a formula for binomial expansion. And if we look here, we've got something on the left-hand side, which is in the form 1 plus x to the power of n. Well, look at what we did a second ago. We've rewritten our expression to 4 minus x to the power minus a half. Well, that's great. That's almost in the form that we need here. However, we've got a 4 here instead of a 1. So we need to try and introduce that 1 somehow. So I'm going to write this with a few more brackets to make it clear. Okay, so now we've got this written like this. What we can do is we can factorise out the 4 from this bracket. So we're left with 4 out of the bracket here. And then so we're going to have 1 inside the bracket because 1 times 4 is our 4 here. And we're going to be left here with minus x over 4. And we can see this would work because if we multiply the 4 back into the bracket, the 4's will cancel and we'd be left with a minus x. So that's perfect. And we've still got the power of minus a half. Great, so now the last thing we're going to do is using our indice laws, we can take this to the power of minus a half and apply it separately to the brackets and to this multiple of 4. So doing that, we'll get 4 to the power of minus a half multiplied by 1 minus x over 4 to the power minus a half. Great, now look at this, we can actually rewrite this a bit neater. So 4 to the power minus a half, we can write as 1 over the square root of 4. And actually, the square root of 4 is just 2. So it's just a half. So now using this here, we can carry out a binomial expansion using the formula from the formula booklet. Brilliant, so I'm going to write it out here, and I'm actually going to write it out like this. We've got 1 plus minus x over 4, to power minus a half. And this just to make it clear, because we can see up here that we've got 1 plus x, and we've got a plus x here. So this means essentially our x term from here, we need to match up with the minus x over 4 here. So I've written it like this with the plus here, so we can clearly see and remember to include the minus here. So we've got half multiplied out. As we can see, the first term is 1 plus n times x, so n is minus a half. And x, and remember we need to include the minus, we've got minus x over 4. And the third and final term that we need to include, so we've got minus a half, multiplied by minus a half minus 1, which is minus 3 over 2. And that's over 1 times 2, which is just 2. And that's multiplied by minus x over 4, all squared. And then this will just carry on. However, in the question it says we only need to go up to the first 3 terms, so that's all we need to work out. Now we're going to multiply out these brackets a bit and tidy it up. So again, we've still got the half and the 1 here. Okay, so the minus a half multiplied by minus x over 4. It's going to x on the top over 8. Add it onto here. So I'm going to do this in a couple of steps. So we're going to multiply out the numerator. So we'll get 3 over 4. That's all over 2. And if we rewrite that out, that's the same as saying 3 over 8. That's multiplied by, so if we square this, we get x squared over 16. And in the numerator, we get 3x squared, and 8 times 16 is 128. So we get 3x squared over 128 here. And again, that carries on. So lastly, I'm just going to multiply through the half. So we're going to have a half plus, so that's going to be x over 16 plus 3x squared over 128 times 2, which is 256. Fantastic. And looking back up at the question, it says we need to give each coefficient in its simplest form. And looking down here, we can actually check this, but all these coefficients are already in the simplest form. So this right here is our answer. So the first 3 terms of the expansion of 1 over the square root of 4 minus x is a half plus x over 16 plus 3x squared over 256. So looking back in the question to see where we get the marks. So we get the first mark here for carrying out the algebraic manipulation and writing 1 over the square root of 4 minus x in this form. We get the second mark for using the correct binomial expansion from the formula booklet. We get the third mark for this line, so for writing out everything in the brackets here. We get the fourth and final mark here for the correct first 3 terms in the expansion. So now I'm going to have a look at part B. So the expansion that we found in part A can be used to find an approximation to root 2. Possible values of x that could be substituted into this expansion. So they've listed out some possibilities here. And part B says, without evaluating your expansion, in part 1 we need to state giving a reason which of the 3 values of x should not be used. In part 2 we need to state giving a reason which of the 3 values would lead to the most accurate approximation of root 2. Right, so we're going to have a look at tackling part B. I first. So we need to give a reason and state which of the possibilities that they've listed up here should definitely not be used. And we see here that I've put a little snippet from the formula booklet again. So it's the same snippet that we used in part A. And this is a crucial bit here. The modulus of x needs to be less than 1. Okay, so that's great. So we can work with that. Now from part A, using this formula, we expanded this. Now we see here matching up the parts. The x here is equivalent to the minus x over 4 here. So essentially what we're saying is for this expansion, the conditions are the modulus of minus x over 4 has to be less than 1. Just making it clear, that's because here we've got the x here and the modulus of x has to be 1. So in our expansion here, essentially this is acting as the x value. So the modulus of minus x over 4 has to be less than 1. Okay, so if we multiply both sides by 4 of the inequality, we get the modulus minus x is less than 4. However, because it's a modulus, we can ignore the minus here because the modulus sort of gets rid of that. So the modulus of x has to be less than 4 for this expansion to be valid. Okay, great. So now we've worked out that condition here. We need to look back up at what they said in the question, which of these aren't valid. But if we think about it, the modulus of x equals 2, well, that's just 2, and that is less than 4. Okay, so that's okay. The modulus of x equals minus a half. Okay, so the modulus of minus a half is a half. Half is less than 4, so that's okay. The modulus of x equals minus 14. So the modulus of minus 14 is 14, and 14 is bigger than 4. So no, that's not okay. So writing this out formally, the modulus of minus 14 equals 14, and 14 is bigger than 4, which means x equals minus 14 should not be used, since x equals minus 14 is not valid for the modulus of x is less than 4. Now take a look at B part 2. Now we need to state which value of x will lead to the most accurate approximation of the square root of 2. Now we get the most accurate approximation when we have a value of x which is the closest to 0. See here that we've already ruled out x equals negative 14, because in B part 1 we said that that's not valid. And look at the other two parts, we see, okay, we've got x equals 2 and x equals minus a half. X equals minus a half is closer to 0 than x equals 2. So x equals minus a half will be the appropriate choice. So writing that out formally, we've got x equals minus a half be our choice because it's closest to 0. So both of these were just 1 mark questions. So we get 1 mark here for correctly choosing x equals minus 14 and giving a valid reason. And we get 1 mark here for correctly choosing x equals minus a half and giving a valid reason. Okay, so we're given an expression for f of x, saying f of x equals 2x squared plus 4x plus 9. And part A says we need to write f of x in the form of a multiplied by x plus b all squared plus c, where a, b and c are integers to be found. And this is a 3 mark question. So now essentially what this question is asking us to do is complete the square. Because when we complete the square, f of x will be written in this form. So we're going to do that now. So we're going to start off saying f of x equals 2x squared plus 4x plus 9. And we've got a slight issue here because we've got a coefficient of x squared, which isn't 1. So here we've got 2x squared. This isn't too much of an issue because what we can do is we can just factorise out the 2. So we're just left with a single x squared. Brilliant. So what I'm going to do is I'm going to bring the 2 out the front of the brackets. So we're left with x squared plus 2x. Now what I could do is divide the 9 by 2 as well and bring that into the bracket. However, because it's an odd number, that wouldn't work out very well. So actually I'm just going to close the bracket here and leave the 9 on the outside, which works absolutely fine. So now we've done this, we can just complete the square on what's inside the bracket here. So doing that, I'm going to put a square bracket here so we can easily see this. And we're left with x, and then we need to divide the coefficient of x by 2. So dividing 2 by 2, we just get 1. We square that. And then we take away this number squared. So it's 1 squared. However, 1 squared is just 1. So we're just going to write 1 here. Brilliant. Now I'm going to close the square bracket off and just keep the 9 here on the end. Now what I'm going to do is multiply the 2 back through into the bracket. So we've got 2x plus 1 all squared minus 2 plus 9. And then the last thing I'm going to do is I'm just going to tidy it up. We've still got the 2. X plus 1 squared, and we're left with a plus 7 on the end. Right, so looking to see where we get 3 marks. We get 1 mark here, and you correctly identified that A would be 2. We then get a second mark here, because then we've correctly identified that B would be 1. And then we get the final mark down here, where we've correctly identified that C would be 7. Great, so now for part B, we need to sketch the curve with the equation y equals f of x, showing any points of intersection with the coordinate axes and the coordinates of any turning points. And again, this is 3 marks. Okay, so y equals f of x, so I'm going to write it out as an equation of y. So we've got y equals, and we completed the square in the previous part. And because they sort of follow and link to each other, I'm going to write it out in the completed the square form because I think this would be helpful. So I'm just going to have a think about what sort of shape the graph could be. So we know f of x is a quadratic and that it's got a positive coefficient of x squared. So we know that the graph is going to look something like this, something like a smiley face. However, to sketch this, we need to find out any points of intersection and the coordinates of the turning points. Well, let's think about points of intersection first. So you've got the y-intercept when x equals 0. So we're going to try that. We would say y equals 2. And if we set x equal to 0, we've got 0 plus 1 squared plus 7, which equals, okay, so that's 2. And this bracket would just turn out to be 1. So we can ignore that, and that would be 7 plus 2, and that would be 9. So therefore, the y-intercept is going to be at 0, 9. So we're going to think about the x-intercept. So the x-intercept when y equals 0. So if we say 0, so we set y equal to 0, so 0 equals 2. X plus 1 squared plus 7. Okay, so if we take away 7 from both sides, we've got that 2x plus 1 squared equals minus 7. So then x plus 1 squared dividing both sides by 2 is minus 7 over 2. We've run into a slight issue here because we've got a negative this side. However, to solve for x, we're going to need to square root both sides. And we can't square root a negative number. Therefore, we can't solve this. And so the curve doesn't intersect the x-axis. Or you could also say that it has no real roots. Okay, brilliant. So we worked that out. The last thing we need to sort out is if there are any turning points. And this is great because there's a little trick we can use in a form once we completed the square. So when we've got something that's in the form y equals x minus a squared plus b. So this is the form you get when you complete the square. The turning point is AB. Well, that's great because our curve is actually in that form, so we can easily work that out. So we've got y equals and 2x, and now we've got x plus 1, but I'm going to write it as minus 1, because that just makes it easier to visualize, squared plus 7. Okay, so look at that, we can see that the turning point will be at minus 1, 7. So now using this information, we're going to actually sketch the curve on this set of axes here. So the first thing we know is the y-intercept, and that's at 0, 9. So that's roughly here. And it's just a sketch, so we don't need to be too accurate, as long as we label our points. And we know it doesn't cross the x-axis, because there are no real roots, so we don't need to worry about that. And look at the turning point. Okay, that's at minus 1, 7. So you know that's in this quadrant here. And I'll say that's about here, so minus 1, 7. I'm going to carefully draw a U-shaped curve going through those points. Fantastic. So now looking to where we get the 3 marks. We get all the marks from on the graph. So we get 1 mark here for having the correct y-intercept, so 0, 9. We get the second mark for the correct turning point, so minus 1, 7. And then we get a third mark for it correctly being a U-shaped curve. Okay, so we're going to have a look at part C now. So part C1 just says, describe fully the transformation that maps a curve with equation y equals f of x onto the curve with equation y equals g of x, where g of x equals 2, multiplied by x minus 2 all squared, plus 4x minus 3. And down here I've also written our answers to part A and part B, which we worked out a second ago, just in case you want to refer back to them. Right, so the first thing we're going to do is have a look, because we've written out f of x in a couple of different ways. So we've written it out like this. But it's also written out like this originally in the question. And we're going to have a look at g of x to see which one would be best to work with. So look at g of x in the question. We see here it's 2 multiplied by x minus 2 all squared plus 4x minus 3. And we can see here we've got 4x. And here in this form of f of x, we've also got 4x. So I think this one will be the easiest one to work with. So that's what I'm going to do. Let's write down f of x here. And g of x. We need to try and work out a transformation that gets us from f of x to g of x. Now this is quite good because they're in similar form. We've got 2 multiplied by something squared. 2 multiplied by something squared. We've got 4x, and then we've got a constant and a constant. The difference here is we've got an x here and x minus 2 here. So the first thing I'm going to try is actually, we've got x going to x minus 2. So if I try f of x minus 2, we're going to see what we get. So f of x minus 2, we get 2 x minus 2 squared plus 4x minus 2 plus 9. And that equals 2 x minus 2 squared. And I'm going to leave it like this and not expand it because that's actually what we want in g of x. And I'm going to try expanding this bracket. So we're going to have plus 4x minus 8 plus 9. And if we just tidy it up at the end, we've got 2x minus 2 squared plus 4x plus 1. Okay, so that's looking good actually, because if we compare our f of x minus 2 to g of x, well, we've got the same term here. They both got 4x. The only difference is a constant. The difference between this and this is 4. So what I'm now going to try is f of x minus 2 minus 4. So we're going to see what we get when we do that. So we get 2 x minus 2 squared plus 4x minus 2 plus 9 minus 4. So we've got 2 x minus 2 squared plus 4x minus 8 plus 9 minus 4. And that equals 2 multiplied by x minus 2 squared plus 4x. And if we tidy this all up here, we get minus 3. I know that's great because actually this matches up exactly to what g of x equals. That means, so writing this out a bit clearer, g of x is actually equivalent to f of x minus 2 minus 4. So that's perfect. Now we just need to try and work out what transformation this represents. Now I'm going to think of some transformations in general. In general, if we have f of x minus a, that is a translation by vector a0. Or if we've got a transformation which is f of x, say plus b, that's a translation by vector 0b. Using that, we could essentially say that this 2 is our a term, and this minus 4 is our b term. So therefore, the transformation that maps y equals f of x onto y equals g of x is a translation by vector 2 minus 4. Right, so we're going to take a look at the final part, part C, part 2. And we need to find the range of this function h of x, where h of x is defined as being 21 over 2x squared plus 4x plus 9. I've also copied in our answer to part B here because that might be useful in a minute. So the first thing to notice is that if we write out h of x like this, the denominator of h of x is actually f of x. So we can rewrite this out actually as h of x equals 21 over f of x. Okay, and that's really useful because we've actually got a sketch of the curve of f of x right here. So we sort of look at that to see what the behaviour would be. Now the first thing I'm going to think about is as f of x tend towards plus or minus infinity, we're going to see what happens. So as it tends towards plus or minus infinity, you see it just keeps going, getting bigger and bigger and bigger, and it just won't stop. It will just keep going, getting bigger and bigger, both in the positive and the negative direction. And this is good because f of x on the denominator, and so if it's f of x tend towards infinity, because it's on the denominator, if you divide by a big number, you get a really small number. So this means that as f of x tends towards infinity, h of x tends towards 0. Because as f of x get bigger and bigger and bigger, you're dividing by a bigger and bigger number each time, which means h of x is getting closer and closer to 0. Okay, so we can start to write down our range of h of x here. So we know that it could go down to 0. Now it can never get to 0, so it's only less than, it's not less than equal to. So the lower bound of our range is 0. Now I want to think about what the maximum value is, so what the upper bound of the range of h of x could be. Now, well, we get the largest value when we divide by the smallest value. So when f of x is minimum, that's when we're going to get the largest value of h of x. Actually, that's perfect, because right here, this is the minimum point of f of x. So down here I can write, so we've got the maximum h of x when f of x is at its minimum. And we see when it's its minimum, we've got a 7 here. So what I'm going to do is do 21 divided by 7, which equals 3. Okay, great. So the maximum that h of x could be is 3, and it could equal 3, so we're going to write it like this. Brilliant. And now this is the answer. So we finished the question. This is the range of h of x. So looking to see where we get our 4 marks in question C. We get 2 marks for the correct vector. So saying that it's a translation by this vector. If we'd only got one of these values correct, then we'd only get 1 mark. And here we get 1 mark for this. So working out that we'll get the maximum value of h of x when we've got the minimum value of f of x. And the minimum value of f of x is 7. So working out 21 divided by 7 equaling 3. And then we get the final mark for the correct range of h of x. So part A says we need to solve for this range of values of theta, the equation 5 sine 2 theta equals 9 tan theta, giving answers where necessary to 1 decimal place. And it also says here, solutions based entirely on graphical or numerical methods are not acceptable. So we're going to need to use some algebra to complete the question. And this is a 6 mark question. And first I'm just going to write down the equation that we've been given. So that's 5 sine 2 theta equals 9 tan theta. Great, so we need to look at that and see if we have any thoughts about what we can do. Well, the first thing that jumps out to me here is we've got sine 2 theta, and in the formula booklet there's actually an identity for that. So using the identity, that sine 2 theta equals 2 sine theta cos theta, we can then rewrite the equation replacing sine 2 theta with 2 sine theta cos theta. Now the next thing that jumps out to me is that it's quite busy. We've got sine theta, cos theta, and tan theta. So to simplify it down a little bit, I'm going to replace tan theta as sine theta over cos theta. We can rewrite this. I'm going to multiply out the bracket at the same time. Right, so now I want to get rid of this fraction here, so I'm going to multiply both sides by cos theta. So we're going to be left with 10 sine theta cos squared theta equals 9 sine theta. So look at this, the temptation could be to see that, we've got a sine theta on both sides. So I'm going to divide through by sine theta and cancel it from both sides. However, we can't do that. We've got to be really careful because we can't divide by 0. And in this case, sine theta could be 0. So we can't just divide through by it because we'd be losing solutions. When you divide through by 0, odd things can happen and you can lose solutions and not get the correct answer. So we need to be really careful. So what we're going to do instead is we're going to bring the 9 sine theta over to the other side by taking it away. So we're left with 10 sine theta cos squared theta minus 9 sine theta equals 0. And then we're just going to factorise out the sine theta. So we've got sine theta multiplied by 10 cos squared theta minus 9 equals 0. So this is great. Look at this. We can now say that, okay, sine theta equals 0 or 10 cos squared theta minus 9 equals 0. So that's 10 cos squared theta equals 9. So cos squared theta equals 9 over 10. And if we square root both sides, that leaves us with cos theta equals, and because we're square rooting it in an equation, we're left with plus or minus, and the square root of 9 is 3, so it's 3 over, and then it's going to be the square root of 10. Okay, so from the original equation, we've got both of these now, which are going to be much easier for us to solve. So starting with the sine theta equals 0 here, we say that theta equals inverse sine of 0, which actually, if you just put that in the calculator, you'll see that's 0 degrees. I'm just going to work with the cos theta quickly now, and there are actually a couple of things we can do here. So we're going to have that theta equals inverse cos of positive 3 over root 10, or theta also equals inverse cos of negative 3 over root 10. Which then, if we put these in the calculator, we get, and in the question it says to one decimal place, so we're just going to give it to one decimal place, we get 18.4 degrees and 161.6 degrees. However, our calculator doesn't give us all the solutions, so we've been given these three solutions to work with. However, there are more than this. So you might be able to see down here, I've drawn the sine and the cos curves, and using these we can find the other solutions. So our range is between minus 180 degrees and 180 degrees inclusive, it tells us in the question. So starting off with this, so theta equals 0. So look at this. Okay, so at theta equals 0, we can also see that there's a solution at 180 degrees and minus 180 degrees. Okay, so up here I'm just going to start writing out all our final solutions. So we've got what we originally worked out, so 0 degrees. And from looking at the sine curve, we got that actually also 180 degrees and minus 180 degrees of solutions. And we're going to take a look at both these now. So 18.4, well, that is somewhere about here. So we can see, okay, so we've got one of the solutions here. But if we work back here, we see it also across here. Okay, we see because the cos curve is symmetrical, this point here is 18.4 degrees. So this one's at minus 18.4 degrees. So we've got another solution at minus 18.4. So writing both of those on, we've got 18.4 degrees minus 18.4 degrees. And last but not least, we're going to work with 161.6 degrees. So that's somewhere between 90 and 180 here. So we've set it's about there. And working down, we can see, okay, so we have one of our solutions here. But drawing a line across here, we've got another one all the way over here. And again, because the cos curve is symmetrical, here it's 161.6 degrees. So here it's going to be minus 161.6 degrees. So writing both these on, we've got 161.6 degrees and minus 161.6 degrees. And this is our final answer. So these are all our solutions to the original equation. So quickly look back through to see where we'll get the 6 marks from. We'll get the first mark for using both of these identities here. So getting down to this line here. We get the second mark here, so for creating this equation here. And then we get another mark here for both this and this, so saying theta equals the inverse. And then we need both the positive and negative versions of these. And then we get the rest of the marks for getting the correct values for theta. And if we got some of them right and not others, that's when you'd get either 1 or 2 marks. Because we got all of them, we're going to get all 3. So we're now going to take a look at part B. So part B says deduce the smallest positive solution to the equation 5 sine theta of 2x minus 50 degrees equals 9 tan theta of x minus 25 degrees. And that's for 2 marks. So first thing I can see is that this equation in part B is actually very similar to the equation in part A. The difference being that theta has been replaced with x minus 25. So what I can do right down here is I can actually say that theta equals x minus 25 degrees. And we can just check that to see that's also true for this bracket, because we've got the 2 theta equals 2x minus 50. So that would mean that theta equals x minus 25 degrees. Which is what we've got here. Now I'm just quickly going to rearrange that. So we've got x equals theta plus 25 degrees. And now up here I've got our answer to part A. So these are all the possible values of theta. And we need to think about which value of theta to use to get the smallest possible value for x. And just by looking at it, the one that it's going to be is minus 18.4. So we're going to sub theta equals minus 18.4 degrees, which is going to give us x equals minus 18.4 degrees plus 25 degrees, which means x equals 6.6 degrees, which is our final answer. So looking to see where we get the marks, where we get 1 mark for attempting to solve this equation here, and then we get the second mark for the correct value of x. Okay, so in a simple model, the value v pounds of a car depends on its age, t, which is measured in years. And we've got the following information available for car A. Its value when new is £20,000, and its value after 1 year is £16,000. So we see here the value is going down, which would make sense in the context of the question, because when you buy a new car, after time the value will eventually go down. So part A says we need to use an exponential model to form for car A a possible equation linking v with t, and this is a 4-mark question. Brilliant. So the first thing we're going to write down is v equals a multiplied by e to the power of k multiplied by t. So this is our general exponential model. And what we're going to do, we're going to work out what the constant a and what the constant k are using the information from these 2 bullet points up here. Okay, so the value when it's new is £20,000. So when it's new, there's going to be no age in it. So then t is going to equal 0. And after 1 year, t is going to equal 1, because we know that t is measured in years. So use this information here. When car is new, we've got the 20,000 equals a e to the k multiplied by 0. And we know anything to the power of 0 is just 1. So that means you just have a multiplied by 1. So therefore, a equals 20,000. Brilliant. So we can write our updated model here. So we have v equals 20,000 multiplied by e to the power of kt. So now we need to work out what k is, and we're going to use the second bullet point for that. So after 1 year, the car is worth £16,000, and that equals, so we worked out that a is 20,000, and that's multiplied by e to the power of k, and then we know that in this case t is 1 because the car is 1 year old. So then we've got the 16,000 equals 20,000 multiplied by e to the power of k. So we're going to make e to the k the subject. So divide 16,000 by 20,000, which gives us 4/5. And now we want to make k the subject. So what we can do is take the natural logs of both sides. So if we do the natural log of e to the k equals the natural log of 4/5. What then happens is the natural log of e just becomes 1. So we've got that k equals the natural log of 4/5 like this. And actually if we evaluate that into the calculator, so just put the natural log of 4/5, we get, I'm going to put it to sort of 3 decimal places, we get minus 0.223. This is a good sign. It makes sense we've got a negative number here. Because as we know, the value of the car is decreasing as the years increase, which means we've got exponential decay here. For that to happen, we know we're going to need to have a negative value for k in our model. Bring all this information together, we can write a possible equation that links v and t. So we're going to say v equals 20,000 multiplied by e to the power of minus 0.223 t. And that is our final answer. So having a quick look through to see where we get the marks. We get the first mark for using a model such as this. We get the second mark here for substituting in that t equals 0 and v equals 20,000, working out the correct value for a. We get the third mark here for substituting in that t equals 1 and v equals 16,000 and working out a value for k. And we get the final mark here for getting a correct equation that links v and t. So look at part B now. It says the value of car A is monitored over a 10-year period. Its value after 10 years is £2,000. And part B says we need to evaluate the reliability of our model in light of this information. And this is for 2 marks. So first you're going to see that it's a value after 10 years. So we're going to need to look at when t equals 10 because t is measured in years. And we see down here I've written our answer to part A. So this is the model we created in part A. The first thing I'm going to do is just look at what value would our model say the car should be at after 10 years. So I'm going to say V equals 20,000 multiply E to the power of minus 0.223 multiplied by 10, because we're looking after 10 years. And putting that in the calculator, we get £2,150. Okay, so in the question it tells us the actual value after 10 years. And the actual value of car A after 10 years is £2,000. And look, these are actually quite similar. 2,150, which is what our model suggests, is approximately equal to £2,000. And in fact, £2,000, if you put 2,150 to one significant figure, you get £2,000. So I'd say, therefore, our model is reliable. So looking to see where we get the marks, we get 1 mark for our work up here, so substituting in t equals 10, and then getting v to equal 2,150. And we get the second and final mark for our conclusion here, saying because they're approximately equal to each other, the model is reliable. Right, so we're going to have a look at part C. Now the following information is available for car B. It has the same value when new as car A, so same value when t equals 0, and its value depreciates more slowly than that of car A. And part C says we need to explain how we could adapt the equation found in part A so that it could be used to model the value of car B, and that is a 1 mark question. Now I'm quickly going to write down to remind us sort of the general exponential model, so that's v equals a e to the power of k times t. Now the key bit of information that we've got given in the question is that car A and B both have the same value when they're new, so when t equals 0. That means we know for the model for both car A and B, it will have the same A value here, so it will be 20,000. So the only other thing that we can adjust is the k value. So formally writing this down, we say that the A value will be the same for car B, since car A and B have the same value when new. So we're going to adapt the equation really by changing the value of k. Now the key bit of information here is that the value depreciates more slowly. Therefore, our k value will need to be closer to 0, so less negative. So the more negative the k value is, the quicker the value would depreciate. So we want to reduce the k value to be closer to 0 than for car A, which is minus 0.223. So writing that out, we want to make minus 0.223, or the k value, less negative. That's all we've got to say to get the 1 mark for part C. So figure 2 shows a sketch of part of the curve with the equation y equals x multiplied by x plus 2 multiplied by x minus 4. The region R1 shown shaded in figure 2, so that's this region here, is bound by the curve and the negative x-axis. And part A says we need to show that the exact area of R1 is 20 over 3, and that's for 4 marks. So the way to find the area under a curve, which is what R1 is, it's an area that's under a curve, we need to integrate. And what we've got the equation of the curve here. We need to know the limits of integration. So when you integrate between A and B. However, we need to know what those values are. So in the case of finding the area R1 here, we need to know this point and this point here. So we need to try and work out what the roots of this curve are, or where it crosses the x-axis. So to do that, we're going to use the equation of the curve they gave us here. And it's actually really useful because they've already given it to us in factorized form. So it's much easier to work out what the roots are, or the x-intercepts. So to work them out, what we need to do is set y equal to 0, because at all these points along here, y is at 0. So if we just set y equal to 0, we can then solve for x. So if we do that up here, we've got the 0 equals x multiplied by x plus 2 multiplied by x minus 4. Here we've got the x equals 0. We've got the x plus 2 equals 0. Or x minus 4 equals 0. And making x a subject in all of those, we get these 3 roots. So we've got x equals 0, x equals minus 2, and x equals 4. So we can work out which ones those are on the graph. So this one is x equals 0. this, because it's on the negative side, must be x equals minus 2. And this is the one that's left over, so that's x equals 4. Now we need to work out the area of R1, we're going to integrate between minus 2 and 0. Now the last thing we're going to do before carrying out the integration is see what form we've got the equation of the curve in. Because at the minute it's in factorised form, which was helpful for what we just did, so like working out the roots. However, it's not very helpful for integration. It's much easier if it's sort of the brackets are expanded. So we're going to do that now quickly. So we're going to expand the brackets. To do that here, we've got y equals. And if I expand these two brackets first, we're going to have x squared. And then we've got minus 4x plus 2x. So it's minus 2x. And then we get minus 8 there. And then I'm just going to multiply the x through into the bracket. So we're going to have x power of 3 minus 2x squared minus 8x. So now I'm going to carry out the integration to find the area of R1. So we're going to integrate x power of 3 minus 2x squared minus 8x with respect to x. And this is going to be between minus 2 and 0. So doing that here, I'm going to put some square brackets. Now, we're going to integrate each term individually. So starting with the first one, we're going to add 1 to the power. So we get 4 and then divide by it. So we get a quarter, x to the power of 4. And then for the next one, again, we're going to add 1 to the power. So we get 3 and divide by it. So we get minus 2 over 3, x power of 3. And again, for the last one, so we're going to divide by 2. So we get minus 4 x squared, and that's between minus 2 and 0. Great, so we're now going to evaluate this up here. So we're first going to sub in x equals 0. We can see we've got an x in each of these three terms, so it would just go to 0. So when we sub x equals 0 in, actually just goes to 0. And then we're going to take away, and then we're going to sub in x equals minus 2. So doing that, we get a quarter minus 2 to the power of 4, minus 2 over 3, minus 2 to the power of 3, minus 4, minus 2 squared. And one thing to note is that these brackets are really important because we're taking away all of this. So it's really important to remember the brackets. Right, so now if we evaluate this, so I'm just going to put all of this into the calculator, we're going to see what we get. So we have minus multiplied by, and if you put that into the calculator, you get out minus 20 over 3. And that's actually great because the last thing we're going to do is we're going to multiply the negative into the bracket, which gives us positive 20 over 3 as needed. So that's fantastic. We completed part A. So we're just going to see where we get our 4 marks from. So we get the first mark here. So expanding out the brackets into a form which is more appropriate for integration. We get another mark for this line down here. So working out that what we need to do is integrate between minus 2 and 0 and integrating the curve. We get another mark for actually carrying out the integration. So the key part is everything inside the bracket here. So we've correctly integrated. And then we get the final mark for all of the rest of the working here. And the key part is this here. So where we've subbed in minus 2 and written it all out like this. We can't just skip to the answer because it's to show that question. So we need to make sure that we're showing each part of our working line by line to get all the marks. The region R2, also shown shaded in figure 2, is bound by the curve, the positive x-axis, and the line with the equation x equals b. So that's this region here in figure 2, and this is the line here, x equals b. B is a positive constant between 0 and 4. Given that the area of R1 is equal to the area of R2, we need to verify that b satisfies the following equation. So b plus 2 squared multiplied by 3b squared minus 20b plus 20 equals 0. And again, this part is for 4 marks. So like in the previous part, we're working with areas under curves. So again, we're going to be dealing with integration. So setting up an integral for finding out the area of R2, we need to integrate between 0 and b to get the area of R2. So if we do that, if we integrate between 0 and b, and then it's the same curve as before, and actually in the previous part here, we expanded out the brackets to get the equation of the curve in this form, because it's just easier to integrate compared to the factorised form in the question. So I'm going to use the expanded form here. So we're going to integrate x power of 3 minus 2x squared minus 8x with respect to x. Key part here is that the area of R1 is equal to the area of R2. And because we know the area of R1 is 20 over 3, we could be tempted to put here, okay, so that's going to equal 20 over 3. However, we need to be careful because that's not actually going to be the case. R1 is above the x-axis, so when we find the area under the curve, the integral evaluates to be positive. However, R2, whilst the physical area is 20 over 3, because it's below the x-axis, it's actually going to be negative. So this will evaluate to minus 20 over 3. Fantastic. So now we've set this up, we can start working with it. So I'm going to carry out the integration, and this is actually exactly the same as in the previous part. So we get a quarter x power 4 minus 2 over 3 x power 3 minus 4x squared. And that's between 0 and b. And again, that equals minus 20 over 3. And evaluating this, we're going to sub x equals b and then take away subbing in x equals 0. So doing that, we'll get a quarter b to the power 4 minus 2 over 3 b to the power 3 minus 4b squared. And actually, we can see there's an x in each of these individual terms, which means when we sub in x equals 0, it's just going to go to 0. So I can just write minus 0. And that equals minus 20 over 3. And here we've just written that in a bit of a more succinct form. One thing I noticed here is that we've got quite a lot of fractions. And I don't really like that because that's quite hard to work with. So we're going to try and get rid of that. So first thing I'm going to do is I'm going to times both sides by 3. And that's going to get rid of these fractions here. Okay, so that's 3b to the power 4 over 4. So for the next term, the 3's cancel, so we're just left with minus 2b to the power 3. And then we get minus 4 times by 3, so minus 12b squared. And then again, the 3's cancel. So we're going to get minus 20. Okay, so lastly, we've got this fraction here. So if I multiply both sides of the equation by 4, the 4 is going to cancel, so we get 3b to the power 4 minus 8b to the power 3. 4 times minus 12, we get minus 48b squared, and that equals minus 80. And lastly, just adding 80 to both sides to set the equation equal to 0. Fantastic. Now looking back up at the question, it says that we need to verify that b satisfies this equation here. And now to do that, we could start working with this equation here, trying to factorize it down until we reach the form of the equation in part b. However, that looks quite difficult. So instead, what I'm going to try doing is expanding out this equation here in part b and seeing what we get. And if this matches what we've got here, then we sort of met in the middle and we verify that b satisfies the equation. I just want to point out the reason we can do this is that it says verify in the question. So this is a way that we can verify it. We can sort of work backwards and meet in the middle. However, if it didn't say verify and it said show that, it would be better to work with this equation and sort of factorize it out till we get to the desired answer. But the fact that it says verify in this question means I'm going to use this method of working backwards. So expanding the brackets, we get b plus 2 squared multiplied by 3b squared minus 20b plus 20 equals 0. So starting with this bracket here, we'll get b squared plus 4b plus 4 multiplied by 3b squared minus 20b plus 20 equals 0. Now to multiply this out, I'm going to do each term individually. So I'm going to multiply the b squared by each of the terms in this bracket, and these terms, and then these terms. So doing that, starting off with the b squared, we'll get 3b to the power 4 minus 20b to the power 3 plus 20b squared. And moving on to the 4b now, we'll get 12b to the power 3 minus 80b squared plus 80b. And lastly, we'll get 12b squared minus 80b plus 80 equals 0. Great, the first thing that jumps out to me is we can see here, so these 80b's cancel. And then the rest, what I'm going to do is just going to group like terms. So get 3b to the power 4, and then grouping them by their powers, we get minus 8b to the power 3 minus 48b squared. And we're left with the constant in the end plus 80 equals 0. And that's fantastic because these equations exactly match, which means we verify that b satisfies the equation. So I'm just going to write something down here to succinctly explain that. Since equations a and b are identical, we have verified that b satisfies the equation. So looking to see where we'll get the marks, we get our first mark for this line here. Then we get the second mark for deducing this here, so going through these steps to write it in this form. And then to get the rest of the marks, you could take either approach. So you could either factorise this down until you get to this equation, or taking the approach that we did, we can successfully expand this equation here and then state that we verified it because both of the equations are identical. So lastly, we're going to take a look at part C. So the roots of the equation 3b squared minus 20b plus 20 equals 0 are 1.225 and 5.442 to 3 decimal places. The value of b is therefore 1.225. And in part C, it says we need to explain with the aid of a diagram the significance of the root 5.442. And this is for 2 marks. Well, the first thing to notice that this is actually this here. So these are the solutions to this bracket here. And we've been told in the question at this point, so we've got x equals 1.225. So quickly, thinking back to what we did in the previous part, you've got that if you integrate between 0 and b, I'm just going to put y here, but we're integrating the curve with respect to x, and we get minus 20 over 3. And what they've given us here is what the values for b actually are. However, we've got 2 values of b, so we've got 0 and 1.225 of y with respect to x is minus 20 over 3. However, we've also got the integration between 0 and 5.442 with respect to x is also minus 20 over 3. And we want to have a think about why that could be. So this one here makes sense because we know that the area of R2 is 20 over 3. So this one makes sense. However, we've got a second value for b that we also get the same result. And the reason for this is when we're integrating, any areas that are above the x-axis will be positive, any areas below the x-axis will be negative. So I'm going to roughly sketch on where 5.442 is. So that will be somewhere along here, so somewhere past this point, because we know this point is x equals 4. So this is x equals 5.442. So when we're integrating between 0 and 5.442, we've actually got a positive area here and a negative area here. And then when you combine them together, we turn out with minus 20 over 3. So I'm just going to shade this area to make it clearer. So we've got this yellow area here. So when we're integrating, because this area is positive and this area is negative, the net area is also minus 20 over 3. So to get the marks, we need to sort of write this succinctly. The net area between 0 and 5.442 is minus 20 over 3. So brilliant. So now this statement also makes sense to us. Now I'm quickly looking to see where we get the 2 marks from. We get the first mark for drawing a sketch of the curve and then drawing a vertical line to the right of x equals 4. So that's what we've done here, so we get a mark for that. And I just copied the diagram across, but in the exam you could just draw a really rough sketch of the curve to get the marks. And then we get the second mark for a correct statement like this, so saying that the net area between 0 and 5.442 is minus 20 over 3. There are also other possible answers you could give for why x equals 5.442 is significant. For example, that between x equals minus 2 and x equals 5.442, then the area above the x-axis is equal to the area below the x-axis. And there are some other statements like that you could give. However, this is the one that I chose. Given that a is bigger than b and b is bigger than 0, and that a and b satisfy the equation log a minus log b equals log of a minus b. And part A says we need to show that a equals b squared over b minus 1, and that's for 3 marks. So looking at this equation, we need to think about if there's anything we can do. And look at this left-hand side, we can see this is actually part of a log law. So using, and we know that log a minus log b equals log of a over b. So we can replace this whole left-hand side of the equation with log of a over b. So doing that, we get log a over b equals log of a minus b. And now because we've just got a single log on each side, so we've got log of something equals log of something, we can then equate both the parts. So we can now say that a over b equals a minus b. Now just an example, if up here we had, for example, a plus 8 here, we couldn't do this because we wouldn't just have a single log something. on each side, we'd have an extra term here. But the fact that, as you can see here, we've just got log of something and log of something, that must mean that it follows that this is equivalent to this. So we can just write a over b equals a minus b. So then next, to get rid of the fraction, I'm going to multiply both sides by b, giving us that a equals ab minus b squared. Now we want to get all the a's on one side. So what I'm going to do is I'm going to, so firstly actually I'm going to add b squared to both sides. So we get b squared plus a equals ab. Then I'm going to take away a from both sides. So get b squared equals ab minus a. And this now means we can factorize out the a. So doing that, we're going to get b squared equals a multiplied by b minus 1. So now lastly what we can do is if we divide both sides by b minus 1, we'll get that a equals b squared all over b minus 1 as needed. And that's everything we need to do to answer part A. And look at the mark scheme to see where we get the marks. We get the first mark up here. So for stating that log A minus log B is log of A over B, and using that fact. We get another mark here for this bit of working. So going from this down to having B squared equals and all the A's on one side. And then we get the final mark for this working here. So factorising out the A and then dividing by the B minus 1, getting A equals B squared over B minus 1. So now part B says we need to write down the full restriction on the value of B, explaining the reason for this restriction. And this is for 2 marks. So we need to have a think about what restrictions there could be on this. Well, the first thing is that we can't divide by 0. So we know that B minus 1 can equal 0. Therefore, B can't equal 1. Because then we'd be divided by 0, which isn't defined. So that's a good start. It also says up here in the question that A is bigger than B, which is bigger than 0. So actually we could use that because we know what A is. A is defined as this. So since A is bigger than 0, we know that B squared over B minus 1 must be bigger than 0. So the thing to notice with this is that we've actually got B squared on the numerator. And if you're squaring something, it's always going to be positive. So we know the numerator will always be positive. And since we know this whole fraction is always going to need to be positive because it's always going to be bigger than 0, we know therefore B minus 1 must be positive. Because a positive, which we know the numerator is always positive, over a negative. So if B minus 1 was negative or less than 0, well, that's going to be less than 0. That's going to be negative because a positive divided by a negative is always negative. So we can write that B minus 1 must be positive or bigger than 0. Therefore, B must be bigger than 1. And that's our final answer. And we see this work we did up here, working out that B can't be 1, is really good. However, we don't need to worry about that because we've now got this restriction that B has to be bigger than 1. So just look at this restriction. It could never be 1. So we don't need to worry about the fact that B can't be 1. We can just stick with this single restriction. We get the second mark for our explanation of this. So this right here is our explanation of why B must be bigger than 1. So let's take a look at this proof question here. So part I says we need to prove that for all values of n contained within, and this means the natural numbers, so the natural numbers, n squared plus 2 is not divisible by 4. And this is for 4 marks. So first we're just going to look through and try and decode the question. So we can see here, okay, so we've got this. And this means the natural numbers, for example, 1, 2, 3, 4, etc. Now there are lots of different methods of proof. However, looking at the question, we try and work out which one would be best. For example, one of the methods is proof by counterexample. But look at this, we couldn't do that because what it says in the question is we need to prove for all n. So we couldn't use a counterexample because that would just be for one particular case. And there are lots of other methods we could think about to see if it will fit. However, the one that fits here is proof by exhaustion. And the reason for this is because we need to prove for all values of n. And what we're not going to do is plug in every single possible value and see if it's divisible by 4, because that's not impossible. There's infinitely many values. So we need to be a bit more clever about this. So a way we could categorize the natural numbers is as odd and even. So we're going to see what happens for an odd number and see what happens for an even number. So we start by looking at for when n is even. And when n's even, we've got a way of writing this. We can say that let n equals 2k. So k being any constant, because if you multiply something by 2, it's always going to be even. So we're just going to see what happens when we plug in an even number. So we're going to say n squared plus 2 equals, okay, so we're letting n be 2k, so that's 2k all squared plus 2, which equals 4k squared plus 2. And this is good because this actually proves that when n is an even number, it's not divisible by 4. And the reason is because here we've got 4 multiplied by some value k squared plus 2. We know that this part is divisible by 4 because 4 multiplied by anything is always divisible by 4. However, then we've got plus 2 afterwards. So something that's divisible by 4, then we're going to add 2 on, which isn't divisible by 4. So we know our overall result isn't going to be divisible by 4. Writing this out as an explanation, we can say, so when n is even, n squared plus 2 is not divisible by 4, since it's 2 more than a multiple of 4, and 2 isn't divisible by 4. So what we now need to do is try for when n is odd. So for when n is odd, and we're going to let n equal. Now, if an even number is 2k, an odd number will just be 1 more than an even number, so 2k plus 1. So that means that n squared plus 2 equals 2k plus 1 squared plus 2, which equals, so we'll get 4k squared plus 4k plus 1 plus 2. And here what we can do is factorize out of 4. So we get 4 multiplied by k squared plus 4. And then combining the constants, we get plus 3. And we see this also, we proved, is not divisible by 4. Because like in the previous example, this term here is divisible by 4, since it's something multiplied by 4. However, we're adding 3 on top of that, which isn't divisible by 4. So we know overall this won't be divisible by 4. And for my explanation here, I've just copied out the same explanation as before, but just changed it to say that when n is odd, and it's not divisible by 4 since it's 3 more than a multiple of 4, and 3 isn't divisible by 4. So here that we've proved, because we've looked at both even numbers and odd numbers, so for any natural number, n squared plus 2 is not divisible by 4. So bringing this all together, we can say that because n is not divisible by 4 when n is odd and when n is even, this means that n squared plus 2 is not divisible by 4 for any n contained within the natural numbers. So looking to see where we get the 4 marks, we get 1 mark for this step here, so testing for when n is even, and we get another mark for our explanation here. And then we get another mark for testing when it's odd. And then we get the final mark for our conclusion both here and also our just general conclusion, saying that this means that n squared plus 2 is not divisible by 4 for any n which is a natural number. So now we're going to take a look at part 2 of this question. So given that x and contained within, and this means the real numbers, the value of the modulus of 3x minus 28 is greater than or equal to the value of x minus 9. You need to state, giving a reason, if the above statement is always true, sometimes true, or never true. And this is for 2 marks. So firstly, just looking at here in the question, it says that x is contained within the real numbers. So the real numbers are just anything that could be represented on a number line. So for example, 1, 3.5, square root of 5. Anything like that is all a real number. Now essentially what the statement is saying is that the modulus of 3x minus 28 is greater than or equal to the value of x minus 9. And we need to state whether this statement is always true, sometimes true, or never true. Now there are a few different approaches we could take to this, but I think a graphical approach will work really well. Now I've drawn out a set of axes here, and what we're first going to sketch is we're going to say that y1 equals the modulus of 3x minus 28. And whenever you're sketching something that's a modulus, it's a good idea to think about it without the modulus sign first, and then we can introduce that. So imagine this without the modulus sign. We're going to sketch y equals 3x minus 28. So the y-intercept is going to be minus 28. So it's going to be somewhere down here. at minus 28. And then just take a quick look to work out where the x-intercept will be. So if we set y1 to be 0, we've got 0 equals 3x minus 28. So 3x equals 28. And x equals 28 over 3, which is around 9.3. So I'm just going to put that somewhere roughly here. So I'm going to say that's 28 over 3. So if I draw that here. So this is the line y equals 3x minus 28. However, we don't have that. We've got y equals the modulus of 3x minus 28. So this means that anything below the x-axis, we need to essentially flip up here. It's going to flip up to create a V shape like this. And this point is just a reflection. So we've got minus 28 here. So it's going to be positive 28 here. So we've got 28 here. And I'm going to get rid of all of this down here. So now we're going to focus on the x minus 9. So I'm going to use a different colour for this. And we're going to say that y2 equals x minus 9. Firstly, looking to see at the y-intercept, well, that's going to be minus 9. So I'm going to sketch that on about here to say minus 9 there. And then working out the x-intercept. If we set y2 to equal 0, we get 0 equals x minus 9. So x equals 9. And 28 over 3 is actually 9.3 reoccurring. So we're just going to be a little bit before that. So if I put that here, and say that equals 9. If I join up those points, we now have the line y2 equals x minus 9. Now we've just quickly sketched that, but one check you can do when you do a rough sketch like this is we can see here we've got a gradient of 3, and here we've got a gradient of 1. And this makes sense because we've got a steeper gradient here and a shallower gradient here. So just make sure that the gradients are the right way around, and that's a good sign that you're on the right track. So now we've done all this sketching, we're going to look back to the question and look at the statement again. So the value of the modulus of 3x minus 28 is greater than or equal to the value of x minus 9. I mean to say whether that's always true, sometimes true, or never true. Well, look at the graph, we can clearly work this out. Between this point here and this point here, the value of x minus 9 is actually greater than or equal to, at these points, than the modulus of 3x minus 28. However, outside of these points, so all the areas over here, the value of the modulus of 3x minus 28 is actually greater than x minus 9, as you can see here. So we can see that sometimes the modulus of 3x minus 28 is greater than x minus 9, and some points, the value of x minus 9 is greater than the modulus of 3x minus 28, and at some points here, it's actually equal. So therefore we know that it is sometimes true. So writing a concluding statement here, we can say therefore, the statement is sometimes true, since there are points where the modulus of 3x minus 28 is less than x minus 9, and points where the modulus of 3x minus 28 are greater than x minus 9. So look at the mark scheme. We get 1 mark for the graph like this, and accurately having the V shape here and the line here, and it intersecting and creating this area here. And then part of the same mark, we needed to state that it's sometimes true. And then we get the second and final mark for the rest of our explanation here. So a competitor is running a 20-kilometer race. She runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer, and after the first 4 kilometers she begins to slow down. In order to estimate her finishing time, the time that she will take to complete each subsequent kilometer is modelled to be 5% greater than the time she took to complete the previous kilometer. So using this model, part A says we need to show that her time to run the first 6 kilometers is estimated to be 36 minutes and 55 seconds, and this is for 2 marks. So to work out the total time for the first 6 kilometers, we need to have a look back in the question at some of the detail. We see she runs the first 4 kilometers at a steady pace of 6 minutes per kilometer. So we can write this down here. We can say, okay, so this would be 6 times 4, because this is the kilometers, and it's going to take 6 minutes to run each kilometer, so it will be 24 minutes in total. However, after that, things change a bit. It says back up in the question that she begins to slow down, and the time she takes to complete each subsequent kilometer is modelled by 5% greater than the time she took to complete the previous kilometer. So adding on to this, we say, okay, it took her 6 minutes to run the previous kilometer, However, it's 5% more than that, so we're going to times it by 1.05. Okay, so far we've got 4 kilometres here, and we've got another kilometre here, so we're going to need to add 1 more kilometre to get to the total time for 6 kilometres. But again, she slows down by 5% again, so it's going to be 6 times, and we need to times it again by 1.05, so we can write that and say 1.05 squared. So working that out by putting it into the calculator, we get 36.915 minutes. However, we want to write that in minutes and seconds, so we know that equals, so we're going to have 36 minutes, and so we got less than another minute, so we got some seconds, so we got 0.915 of a minute, so that's going to be 55 seconds. And the reason for that is because we've got 1 minute, which is 60 seconds, times by 0.915, which equals 54.9, which is approximately 55. So that's great, that's the answer to part A. Moving on to part B, it says we need to show that her estimated time in minutes to run the rth kilometre, for r is between 5 and 20, is 6 times 1.05 to the power of r minus 4. And this is just for 1 mark. So we're just going to write down what we know. So we know for the 5th kilometre, it takes her 6 times 1.05. I'll write that to the power of 1. And we see, because we worked that out earlier, it's here. So she takes 6 minutes, and then it's 5% more than that. So we're timesing it by 1.05. And here we also worked out the 6th kilometre is this here. So the 6th kilometre takes us 6 times 1.05 squared. So it would follow that the 7th kilometre would take 6 times 1.05 to the power of 3. And if we soon work out if there's a common pattern here, we've got, okay, for the 5th kilometre, if we take away the power here, minus 1, we get 4. Okay, the 6th kilometre, we take away the power, we get 4. And the 7th kilometre, we take away the power, and we get 4 as well. So we've basically shown it there. So therefore, it follows that the time taken for the rth kilometre is 6 times 1.05 to the power of r minus 4. And lastly, we're going to take a look at part C here. So we need to estimate the total time in minutes and seconds that she will take to complete the race. And that's for 4 marks. So we know that she runs at a steady pace of 6 minutes per kilometre for the first 4 kilometres. And we previously worked out that that was 24 minutes. So we can write that down here and not worry about that. We can just say total time at the start is going to be 24 minutes. And then we're going to add on top of that. And what we're going to use is this general formula that we created in the previous part. So if we do the summation of that formula, so 6 times 1.05 to the power of r minus 4. And well, here, this is the first 4 kilometres are already taken care of here. So this is 4 kilometres. So for this summation, we want to go from r equals 5, because we look at the 5th kilometre, and it's a 20 kilometre race. So we want to go up to 20 kilometres here. So now the last thing to do is evaluate all this. This right here is actually a geometric series that we're going to evaluate. And to do that, we need to know a few things. So we need to know the first term. Well, the first term is going to be when r is 5. So 5 minus 4 is 1. So that's 6 times 1.05, which equals 6.3. And the common ratio is 1.05. That's because for each kilometre that she's running, we're multiplying by 1.05 because she's taking 5% more time than in the previous kilometre. And we can also say here that n is going to be 16. That's because we've got 20 kilometres in total. We've got 4 kilometres here. So this is evaluating 16 kilometres. And this is basically how many terms there are. So for each kilometre, we've got a new term. So that means n is 16. And then we can evaluate this using a formula from the formula booklet. It says the sum is a multiplied by 1 minus r to the power of n all over 1 minus r. So doing that, we get that the total time equals 24 minutes plus 6.3 multiplied by 1 minus 1.05 to the power of 16 all over 1 minus 1.05. 173.042 to 3 decimal places. Just work that by putting that in the calculator. So that's minutes, and that equals 173 minutes and 3 seconds. And just like earlier, we worked that out by doing 60 multiplied by 0.042 and then rounding to the nearest second. So looking at the mark scheme, see where we get the marks. For part A, we get 1 mark for this line here and 1 mark for the correct answer. So for part B, we get 1 mark for all this working. Essentially what we've got to show is that we're making a link between the rth kilometre and the index here. So that's what we're showing here. And finally, for part C, we get 1 mark for this line here. We get another mark for this part here. So using the correct formula from the formula booklet. Then we get another mark here for adding it on to the 24 minutes to get the total time. And we get the fourth and final mark for the correct answer. So we're going to take a look at this question here. Now it's actually quite a long question, it's 10 marks. So we're going to look at each part individually and gradually build it up. So firstly, just look at part A. We are given that f of x equals 10 multiplied by e to the power of minus 0.25x multiplied by sine x. And we know that x is greater than or equal to 0. And part A says we need to show that the x coordinates of the turning points of the curve with the equation y equals f of x satisfy the equation tan x equals 4. And this is for 4 marks. So the thing that jumps out to me is that we need to find the turning points. And now we know to find the turning points, we need to differentiate because then that will give us the gradient function. And then if we set that equal to 0, we're basically saying wherever on the curve the gradient is 0, and the gradient will be 0 at the turning point. So the first job we have to do is differentiating f of x. So when we differentiate f of x, we get f dash of x like that, so we use that notation. And we can see here we've got a product. We've got this multiplied by this. So what we're going to use is a product rule. And the way I remember this is saying we need to differentiate, hold. So we'll see what I mean in a minute. So firstly, we're going to differentiate this part here. And because we're working with an exponential, what we do is we multiply down the power. So you've got minus 0.25. And then multiply everything how it is here. So that'll be multiplied by 10 e to the minus 0.25 x. And remember, the product rule, we need to differentiate, hold. So now we need to hold or keep the same, so sine x. And then adding on to that, we now need to do it the other way around. So we differentiate the sine x, so we get cos x, and then we hold or keep the same the other part. So that's just 10 e to the minus 0.25x. Brilliant, so I'm just going to write that out a little bit neater here, multiplying out the brackets. Brilliant, so now we've successfully differentiated f of x. So to find the turning points, we're going to set f dash of x equal to 0. So we're going to say 0 equals... Something that jumps out to me here is that we can factorise out the e to the minus 0.25x, because we can see that we've got that in both terms here. So doing that, we get e to the minus 0.25x multiplied by minus 2.5 sine x plus 10 cos x. So therefore, we know that e to the minus 0.25x equals 0, or minus 2.5 sine x plus 10 cos x equals 0. So if we think about this one first quickly, this actually can't be solved, so we're going to reject. And this actually makes sense because if we sketch it out like this, we've sort of gotten a graph, something like that. And actually y equals 0 acts as an asymptote here, and it never touches 0, so it can't equal 0, so there are no solutions. So we're going to work with this here. So first I'm just going to add the minus 2.5 sine x onto the other side. So you get that 10 cos x equals 2.5 sine x. And then what I'm going to do is I'm going to divide both sides by 2.5 and divide both sides by cos x, which means we'll get that 10 over 2.5 equals sine x over cos x. And then since sine x over cos x equals tan x, we can write this. I'm going to write them actually flip the other way around. So we're going to say tan x equals, and then if you put this into the calculator, you get a 4 as needed. Looking to see where we'll get the marks, we'll actually get 2 marks here for successfully differentiating using the product rule. We get another mark down here for both factorising out the e to the power of minus 0.25x and then realising that it doesn't have any solutions, so we need to reject it. And then we get the final mark here for this working here, which leads down to tan x equals 4. So now we're going to take a look at part B. So part B says we need to sketch the graph of h against t, where h of t equals the modulus of t multiplied by e to the power of minus 0.25t multiplied by sine t. And we need to show the long-term behaviour of this curve. And this is for 2 marks. So the first thing to notice is that actually inside this modulus is actually f of x. And that's great because we can see up here, it says figure 3 shows a sketch of part of the curve with equation y equals f of x. And we can see that up here. So the difference with h of t is that it's the modulus of f of x. So essentially what's going to happen is all these negative parts here are going to flip over and be positive like this. It's going to have the same shape of f of x. However, any time that it was going below the x-axis, it's then going to be flipped up to be positive. Looking back at this, I just noticed that I didn't really draw this very well. The one thing to be aware of, that between each loop, the distance on the t-axis should be the same. However, on my graph, as you get further and further along, it looks like the width of them are decreasing. So just be careful to make sure the width along the t-axis is the same. And that will make sense why that's important later on in part D. Taking a look to see where we get the marks, we get 1 mark for the correct shape, and the second mark, we get the second mark for there being decreasing heights. So now look at part C. It says the function h of t is used to model the height in meters of a ball above ground t seconds after it has been kicked. Using this model, we need to find the maximum height of the ball above the ground between the first and second bounce. So here I've just got a smaller version of the graph that we drew in the previous part. This is the turning point we need to identify, because right along here, at this point here, is the height of the ball above the ground between the first and second bounce. And this is because here the ball's been kicked, and then it starts to fall, and here it has its first bounce. So this is the point in between the first and second bounce, and here's the second bounce. So we need to identify this point. Well, what's great is that in part A that we found out that the turning points satisfy the equation tan x equals 4. So we can use that here. So we can say that tan x equals 4. X equals the inverse tan of 4. So if I put that into the calculator, work it out in radians, we get 1.326. However, this is just one of the solutions, and we actually don't want to find the first solution, we want to find the second solution. So I've drawn a quick sketch of the tan graph here to illustrate what we're doing. But if our first solutions, we get 1.326 radians, so about here. Our next solution, we can go along, and it'll be here. And the tan graph repeats every 180 degrees. So because we're working radians, that's every pi. So what we're going to do is get from here over to here. I'm just going to add pi to this. So if we add pi, we get 4.47 to 2 decimal places. And now that's great. So we've worked out what x equals. However, that's not what it's asking us for in the question. We need to find the height. So we need to find not this point, not what x equals. So we need to find this point here. So if we do h of 4.47, that's going to equal, so looking back up at the question, we see that's the modulus of 10 multiplied by e to the power of minus 0.25 multiplied by t, so in this case 4.47, multiplied by sine t, so 4.47. So putting that in the calculator, we get that everything inside the modulus signs comes out to minus 3.18, but because it's modulus, the answer is going to be positive 3.18, and it's in meters. So that is the final answer. For this question, we'll get 1 mark here for realising that we need to solve tan of x equals 4, and then substituting that into h of t. We get a second mark here for substituting the correct value into h of t, and then writing this part out here. And then we get the final mark for the correct answer of 3.18 meters. Lastly, we're going to take a really quick look at part D, where it says explain why this model should not be used to predict the time of each bounce. And the reason for this is that the times between each bounce should not stay the same when the height of each bounce is getting smaller. And this makes sense because the times between each bounce are the same. I haven't drawn it very well here, so it doesn't really show it. However, the model, the times between each one will be the same. However, in reality, they'll get shorter and shorter the more the ball bounces. So we just get 1 mark for this statement here. So the curve C with equation y equals p minus 3x all over 2x minus q multiplied by x plus 3, where p and q are constants, passes through the point x equals 3 and y equals a half, and has two vertical asymptotes with equation x equals 2 and x equals minus 3. In the first part of A, we need to explain why you can deduce that q equals 4. The key bit of information is that we have two vertical asymptotes. Now you get vertical asymptotes when the denominator equals 0, because if you try dividing by 0 you can't, so it creates asymptotes. This means there are vertical asymptotes when the denominator equals 0, so in this case the denominator is 2x minus q multiplied by x plus 3, and that equals 0. So this means that 2x minus q equals 0, or x plus 3 equals 0. So that means here that x equals minus 3, or 2x equals q. So we can see here in the question that we've got x equals minus 3 here, and x equals minus 3 here, so we've sorted that. The only one we haven't sorted is x equals 2. So we know that that one must be related to this right here. So what I'm going to do is just sub x equals 2 into this right here. So we're going to have 2 multiplied by 2 equals q. So therefore, q equals 4 as needed. So now A part 2 says we need to show that p equals 15. So in the previous part we worked out what q equals. So I'm just quickly going to rewrite out the equation for curve C right here, but replacing q with 4. So doing that, we get y equals p minus 3x all over, and we get 2x minus 4, because we're replacing the q with 4, multiplied by x plus 3. Now, a key bit of information in the question is that the curve C passes through the points x equals 3 and y equals a half. So what I'm going to do is sub in x equals 3 and y equals a half into the equation of curve C. So doing that, we're going to get that a half equals p minus 3. So x here is 3, so multiplied by 3 all over. That's going to be 2 multiplied by 3 minus 4 multiplied by 3 plus 3. So evaluating these brackets, we'll get, okay, so that's 3 times 2 is 6 minus 4, so we get 2. And that'll be 6. So times by 6 equals 12. So if I rewrite that out here, we get p minus 9 all over 12. So I'm just going to move over here for our final working. So far we've got that half equals p minus 9 all over 12. So if we times both sides by 12, we're going to get 6 equals p minus 9. So therefore p equals 6 plus 9, just by adding 9 to both sides. So therefore p equals 15 as needed. Fantastic. So looking through to see where we get the marks. We get 1 mark up here for all this working. So essentially explaining that 2x minus q equals 0 when x equals 2, which then means that q would equal 4. So we get 1 mark for that. And then we get 1 mark down here for realising that we need to sub in the points 3 and a half to make sure we've just got p as the single unknown. And then we get the final mark here for then using our algebraic manipulation skills to work down through to show that p equals 15. So we're now going to work through part B. So figure 4 shows a sketch of part of the curve C, and the region R, shown shaded in figure 4, is bound by the curve, the x-axis, and the line with equation x equals 3. Part B says we show that the exact value of the area of R is a, the natural log of 2, plus b of the natural log of 3, where a and b are rational constants to be found. And this is for 8 marks. The first thing I want to do is work out what this point is, because we're going to integrate between x equals 3, but we need to know our upper limit of integration. What's great is in the previous part we worked out what q and what p equals. So now we can write out the equation of the curve C, replacing p and q with the values that they are. So this is the equation of the curve C, where we've replaced q with 4 and p equals 15. So now to work out this point here, this is actually the x-intercept, so we're just going to set y equal to 0. So we're going to have 0 equals 15 minus 3x all over 2x minus 4 multiplied by x plus 3. And if we times both sides by the denominator, we're going to get that 0 equals 15 minus 3x. So 3x equals 15. So x equals 5. So that's great. We've got our first bit of information that we need to know. That this point right here is x equals 5. So essentially, to answer the question, we're going to need to integrate between x equals 3 and x equals 5. And we're going to be integrating the curve C. So we're going to be integrating 15 minus 3x over 2x minus 4 multiplied by x plus 3 with respect to x. So to integrate this, we're going to need to use partial fractions. So we're now going to work on writing this equation in partial fractions. So we're going to say that 15 minus 3x all over 2x minus 4 multiplied by x plus 3. So we've got something a over, and we're going to have 2x minus 4 here. And then we're going to add on to that b over x plus 3. So now our job now is to work out what a and b are. So what we're going to do, we're going to multiply both sides through by the denominator here. So this means it cancels out here, so we just get 15 minus 3x. And these brackets will cancel, so we'll just get a multiplied by x plus 3. And these brackets will cancel here, so we'll just get b multiplied by 2x minus 4. So now we're almost there working out what a and b are. So we're going to take a couple of steps. Firstly, I'm going to let x. And firstly, I want to try and work out what b is first. So we want to try and work out a way to get rid of a. Well, to get rid of it, if you times it by 0, you're going to get rid of it. So we're going to let x equals minus 3, which will mean that this bracket goes to 0, which means we're just left with b and we can solve for b. So here we're going to get 24, because if we sub the x equals minus 3 into here, we get 15 minus 3 times by minus 3, which gives us 24. And then this bracket just goes down to 0, so we can ignore that. And that's going to equal b multiplied by, so 2 times minus 3 is minus 6. And if we take away 4 from that, it goes to minus 10. So therefore b equals minus 2.4. And here we're just going to do the same thing again, but we're going to get rid of b this time so we can work out what a is. So we want this bracket to go to 0. That means we need 2x minus 4 to equal 0. So that means x is going to need to equal 2. So we're going to let x equals 2. So if we sub that into the left-hand side, we're going to get 15 minus 6. So we're going to get 9 equals, and the b gets eliminated because we're just multiplying it by 0. So the a, we're going to have 3 plus 2. So we're going to have 5a. Therefore, a equals 9 divided by 5, which is 1.8. So here I've just written out the partial fractions a bit neater, using our values for a and b that we worked out earlier. So all that's left to do is work out the area of the region R. So we're going to do some integration. So we're going to integrate between, and like we worked out earlier, we've got between x equals 3 and x equals 5 here. So 3 here and 5 there. And we're integrating this curve here, but instead of writing it in this form, we're going to write it in the partial fraction form here. So we've got 1.8 over 2x minus 4 minus 2.4 over x plus 3. And we're going to integrate that with respect to x. Now, one of the rules of integration we can use is that if we're integrating something which is in the form of f dash of x over f of x with respect to x, that will equal the natural log of the modulus of f of x plus c. Now we can use this rule up here for integrating both these terms. For example, for this one here, if we say f of x equals the denominator, so 2x minus 4, f dash of x, so when we differentiate it, will just be 2. Now, we see we've got 2 here, we've got 1.8 here. However, that's not too much of an issue. We can work around that. We just need to work out what multiplier we need to use to get from one to the other. So if we do 1.8 divided by 2, we get 0.9. So we're going to use that as a multiplier to get from one to the other. I'm going to do this for the other one quickly, and then it will make sense what we mean in a second. So for this one, we've got f of x equals x plus 3, and f dash of x equals, so that would just equal 1 when we differentiate. But on the top, we've got 2.4. So what I'm going to do is, again, 2.4 divided by 1. Well, that just equals 2.4. So we're going to use that as a multiplier. So when we integrate it, so this term is going to become, we're going to need to use our multiplier first. So 0.9 multiplied by natural log of 2x minus 4. I'm going to add on to that, integrating this term. And we need to remember we've got the minus sign here. So instead of the plus here, we're going to have minus, and then we're going to have 2.4, so I'll multiply from down here, multiplied by the natural log of x plus 3. And we need to remember our limits of integration, so between 3 and 5. Just quickly want to explain why we've got these multipliers here. So if we imagine we were just differentiating this, we can use the rule we have for integration, but in reverse. So if we're differentiating this, we'll get this. So this means if we just differentiated the natural log of 2x minus 4, we get 2 over 2x minus 4. However, that's not what we want. We want 1.8 over 2x minus 4. So we need to times that by the multiplier 0.9. So if we include the multiplier, we get 1.8 over 2x minus 4 as we need. Great, so lastly, we're just going to evaluate this by subbing in x equals 5 and x equals 3. So we're going to get 0.9 natural log of 2 multiplied by 5 minus 4 minus 2.4 multiplied by the natural log of 5 plus 3. And then we're going to subtract from that. And I'm going to put some brackets in because we're subtracting all of this. 0.9 multiplied by the natural log of 2, and this time multiplied by 3 minus 4, minus 2.4 multiplied by the natural log of 3 plus 3. So tidying this up a little, we'll get 0.9. And then inside the modulus sign here, we'll get 2 times by 5, so that's 10 minus 4, so we get 6. Minus 2.4. And then we get 5 plus 3, so that's 8. And we're going to subtract. And we're going to subtract both terms here. So we're going to get minus 0.9, the natural log. And evaluating this, we get 2 times 3. So that's 6 minus 4, so we get 2. And then because it's a negative times a negative, we get plus 2.4. And the natural log of 6. So we can combine both these terms quickly. So we'll have 0.9 plus 2.4, which equals 3.3. Minus 2.4, ln 8, minus 0.9, ln 2. Right, so now we're almost there, but if we look back up at the question, we see we need to write it in a form where we've only got log of 2 and log of 3. So we've got to manipulate this a little bit more. Well, using some of our log laws, we can say actually this is 3.3. Ln 6 is actually the same as ln 3 plus ln 2. Because the rule is you can multiply these together when you're adding them to combine it into one log, and 3 times 2 is 6. And we've got minus 2.4 ln, and 8 we can actually write as 2 to the power of 3 minus 0.9 ln 2. So first I'm going to multiply out this bracket, so we get 3.3 ln 3 plus 3.3 ln 2. And then here we can use the log law to say we're going to bring down this power and multiply it by the minus 2.4. So doing that, we'll get minus 2.4 multiplied by 3, so minus 7.2. So ln 2. And then minus 0.9 ln 2. So lastly here, we're just going to collect like terms. So we're going to have the 3.3 ln 3. Then we're going to collect all of the ln 2's together. So 3.3 minus 7.2 minus 0.9, which is going to be minus 4.8 ln 2. And that's actually the final answer in the correct form that they wanted. So looking through to see where we get the 8 marks for this question. We get 2 marks here for working through the partial fractions. So work out that we need to do partial fractions and setting up like this and trying to find values for A and B. We get another mark for partial fractions here, so for working out the correct values for A and B and writing out in this form. Then we essentially get 4 marks for the rest of our working here. So integrating successfully and subbing in x equals 5 and x equals 3 and using our log laws to get down to the correct form. And then we get our 8th and final mark for this line here, so correctly identifying there will be 3.3 as the coefficient of ln of 3 and minus 4.8 of the coefficient of ln of 2. So the curve C in the standard Cartesian plane is defined by the equation x equals 4 sine 2y. The curve C passes through the origin. Part A says we need to find the value of dy by dx at the origin, and this is for 2 marks. So I'm just going to write out our equation here. We've got x equals 4 sine 2y. And the first thing I notice is actually we've got x as a subject here instead of y that we'd be used to. So what we're going to do, instead of finding dy by dx, we're going to find dx by dy. So we're going to differentiate everything with respect to y. So we're going to get dx by dy equals, I'm going to have 4 here, multiplied by, if we differentiate sine 2y, we'll get 2 cos 2y. So this equals 8 cos 2y. This is great, however, we need to look at dy by dx, but we've got dx by dy. So what we're going to do is take the reciprocal of both sides. So if we do that, we're going to get the dy by dx, we want on the left hand side, and it's going to be 1 over everything. So 1 over 8 cos 2y on the right hand side. So now lastly, we need to find the value of dy by dx at the origin. So at the origin, it's 0, 0. So x equals 0 and y equals 0. So we're going to sub y equals 0. So doing that, we get that dy by dx equals 1 over 8 cos, and that would be 0 because 2 times y, when we're subbing y to be 0, just goes to 0. Putting that into the calculator, we find that cos of 0 equals 1. Therefore, the value of dy by dx at the origin equals 1 over 8. Therefore, the value of dy by dx at the origin equals 1 over 8. So we'll get 1 mark here for all of this working here. So attempting to differentiate x equals 4 sine 2y, and then taking the reciprocal, so inverting it to get dy by dx. Then we get the second mark here for realising at the origin it's going to be 0, 0, and subbing that in and getting dy by dx equals 1 over 8. So part B1 says, use the small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. Okay, well, our small angle approximation is that when sine x for values of x that are small is approximately equal to just x. So it follows that for sine 2y for small values of y would approximately be 2y. So therefore we say x equals 4 sine 2y, and then using sine 2y is approximately equal to just 2y. So use that, we can say that x is approximately equal to 4 multiplied by 2y. So x is approximately equal to 8y. And that's the final equation linking x and y. For the second part B, we need to explain the relationship between the answers to A and BI. So the value found in part A is the gradient of the line found in part B, part 1. So what we're saying here is that 1 over 8, so what we found in part A is the gradient of this line here. And that would make sense, because actually if we rearrange this to get y equals 1 over 8x, then we can see here that our gradient is 1 over 8, so it makes sense. So in part B, you get 1 mark for this working here, so getting down to x is approximately equal to 8y, and then you get the second mark for this statement right here. Lastly, we're going to take a look at part C. So we need to show that for all points x, y lying on C, dy by dx equals 1 over a multiplied by the square root of b minus x squared, where a and b are constants to be found. And this is for 3 marks. So what I've done here is I've written down some things we worked out in the previous part. So we know that dy by dx equals 1 over 8 cos 2y, and x equals 4 sine 2y. So this is what we're going to use. We're also going to use one other identity. So we know that sine squared x plus cos squared x equals 1. However, it then follows, if we replace all the x's with 2y, we're going to have that sine squared 2y plus cos squared 2y equals 1. So we're also going to use that identity. And using these 3 things, we're going to get dy by dx in that form. And the thing I noticed about this form is we've got dy by dx, and then we've just got x's here. So essentially our aim is to eliminate all of the y's from the right hand side. Firstly, I'm going to work with this and this. So if we square this equation here, we're going to get that x squared equals 16 sine squared 2y. It's great because we've got a sine squared 2y here and sine squared 2y here in this identity. So we can use that to get cos squared 2y instead. So using, and if we rearrange the identity, we're going to get that sine squared 2y equals 1 minus cos squared 2y. We can now say that x squared equals 16 multiplied by 1 minus cos squared 2y. So therefore x squared equals 16 minus 16 cos squared 2y. What I'm now going to do is try and make cos squared 2y the subject. So I'm going to add 16 cos squared 2y to both sides and take away the x squared. So we get 16 cos squared 2y equals 16 minus x squared. If I just divide by the 16, we'll get 1 minus x squared over 16. And if I square root both sides, I'm going to get that cos 2y equals the square root of 1 minus x squared over 16. It's fantastic because we've now got an expression for cos 2y. So we're going to go up here and we can use that. So we're going to work with our dy by dx expression now. So we're going to say dy by dx equals 1 over 8. And we can see here it's 1 over 8 cos 2y. But we know what cos 2y equals, so we're going to replace it with that. So 8 multiplied by the square root of 1 minus x squared over 16. Fantastic, we're getting really close. But if we look up in the question, we can see we need to work a bit to get it in different form because we've just got an x squared here instead of x squared over 16. So I'm going to times both the top and the bottom by the square root of 16. This will mean we get root 16 on top over. I could choose to multiply the root 16 either by the 8 or by the square root here. But if I do this, we're multiplying both the surds together. So we're going to get 8, and then we're going to get the square root. So we get 16 times 1. So we get 16 here. And then this is the crucial bit that here, the 16s cancel. And so we're just left with x squared as it wants in the question. And the last thing to do is actually that this just equals 4. So if we divide the top and the bottom by 4, we're going to get 1 over, and then 8 divided by 4 is just 2. So 2 square root of 16 minus x squared. And then we're finished because that's in the form that wants in the question. So we've got that a is 2 and b is 16. So through we get 1 mark here for all this working down here in an attempt to get dy by dx to have no y's on the right hand side. We then get the second mark for this bit here. So if we get a correct answer for dy by dx. And then we get a final mark right down here for going through these steps to simplify it down into the form that they want.